Barry from Barry Science Lab, and today we'll be talking about integrals in real analysis. Now, you probably recognize the integral as one of two things. Either the area under a curve, or the inverse of a derivative. But in actuality, when we define the integral, we only mean one of these things, the area interpretation. In fact, this interpretation of it being an inverse derivative is actually not an integral at all. It's called an antiderivative. And it is a very lucky fact that these two happen to be the same. But that's something we'll prove in another video. So, how do we actually define integrals? I mean, the area under a curve is pretty unclear. So, let's first say we have a bunch of rectangles. And you probably recognize that from when you were doing Riemann sums in Calculus 2. But we first have to be very careful with our definition of Riemann sums. In fact, what we're about to do right now isn't even technically called a Riemann sum by the textbook I'm using, Basics of Real Analysis by Yuri Libel. I don't know if I pronounced that correctly, but his name is up here, and his textbook is very good, so I'd recommend you use it. So anyway, this textbook does not call that summation of rectangles a Riemann sum just yet, because of one pretty specific reason. So, this textbook actually calls it a Darboux sum. I also don't know if I pronounced that correctly. Probably should have looked that up before I started this video. But basically, you have a bunch of rectangles below a function. But basically is not enough in the world of real analysis. So what do we actually mean when we say we have a bunch of rectangles under a function? Well, essentially, let's start by taking the x-axis, and let's say we're trying to integrate from some point A to some different point B. Remember, the antiderivative notion is completely out of our minds right now. The integral has nothing to do with the derivative at this point in time. So, let's say we're integrating something from A to B. We're finding the derivative under, we're finding the area under that function's curve. So, first, we have to figure out how wide our rectangles are going to be. So, we partition this interval into several little slices. So we call this x0, x1, x2, and there can be as many x's as we want over here, and then xn minus 1, and we let b be xn. And now, here's what we do. We take our specific curve right here, and we essentially look at each specific portion of that curve between xi minus 1 and xi. So, for example, right here is the interval of the curve from xn minus 1 to xn, which is equal to b. By the way, the only condition is that xi must be less than or equal to xi plus 1 for all I, for all I between 0 and n. And the other condition, of course, we've got the boundary conditions, a equals x0 and b equals xn. So, anyway, how do we figure out what the rectangle is going to look like over here? Well, here's the problem. Right here, you can see clearly f of xn minus 1 is bigger than f of xn. So, how do we resolve this? Well, there are actually two Darboux sums. The upper sum and the lower sum. So, what's the upper sum? Well, that's just taking the supremum of the function in this interval. So, for all x in the interval from xn minus 1 to xn, this upper sum, the height of one rectangle that's included in this upper sum is equal to the supremum of all x So the height of each of these rectangles is equal to the supremum of all x such that x is in this interval from xn minus 1 to xn. So, for example, the supremum is, since this is constantly decreasing, this right here for the upper sum. And instead, for the lower sum, we take the infimum right over here. So, for example, if we have an interval right over there, then the infimum is right here, even though it's not at the end of the interval. So we take that as our sum. If instead we want the upper sum, we take the supremum, which is at the left end of the interval. So you can see this very distinct difference. But the thing is, it's one function. It should have one sum. So our Darboux sums only make sense if they converge to one total sum as n approaches infinity, i.e. as these overestimations or underestimations get more and more and more accurate. So we want to make sure that our Darboux integral, which is equal to our Darboux sum as n approaches infinity, our upper Darboux integral, which has a bar on the top right here from a to b, is equivalent to our lower integral. But sadly, for some functions, that's not always true. So let's take the Dirichlet function, for example. If you watched my series about real analysis at Hunter College, you'll know the Dirichlet function is d of x such that if x was a rational number, d of x was equal to 0, and if x was an irrational number, d of x was equal to 1. So, is it rational or irrational? Now, of course, this function is not really continuous, as you can see. And, of course, we proved a lot more properties about it back in my Hunter College series. But right now, we're here to prove that the upper integral of this, the upper Darboux integral, is not equal to the lower Darboux integral.
Isaac, can you do a separate video for this?
What? No. We haven't even gotten started.
Because my hand got a little bit tired, but it's okay.
Okay. For any A and B that are distinct, of course. So, how do we prove that? Well, let's figure out what the upper integral of this from some point A to some different point B is. Well, we have to figure out the supremum of this. Now, here's the problem with that. If B is irrational, well, we have to figure out the supremum of this. And that's actually pretty easy. Why? Because the irrationals are infinitely dense. You take one irrational, you take another irrational, you take their average, and you've got a new irrational right over there. So, what we can do is we can say, in this interval A to B, since A and B are two distinct numbers, there must exist an irrational number somewhere within, which means there must exist at least one point where d of x is equal to 1. And so, we take the supremum of that, and boom. Our upper integral of d of x dx is suddenly greater than 0. Meanwhile, if we take the infimum, well, the rationals are also infinitely dense. So the infimum is obviously going to be 0. So if we take the supremum for everything, it's going to be greater than 0. If we take the infimum for everything, it's going to be equal to 0. Boom, contradicts it. Which means d of x dx does not have one existing Darboux integral. And that means it is not Riemann integrable. That's right. We're finally getting to terms that you probably heard about in Calc 2. Now, how do we give a rigorous definition, an equation we can actually write out for an integral? Well, the Riemann integral of f of x dx from a to b goes like this. Given a, which is equal to x0, like the boundary conditions we stated back there, which is less than x1, which is less than x2, dot, 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 which is less than xn minus 1, which is less than xn. And xn is, of course, equal to b. So then, how do we figure out this integral right here? Well, it's the limit as n approaches infinity of the sum from I equals 0 to n of xi f of xi, delta xi f of xi, where we define delta xi as equal to xi plus 1 minus xi. So this is that famous sum of rectangles we've been hearing so much about. And this dx is essentially the shrinking down of this delta xi, the same way this f of x is the same as this f of x. So this is what a Riemann integral is, and this is what an integral is at heart. So now, how do we reconcile this definition with the antiderivative definition? How do we know specifically that the indefinite integral of f of x dx, how do we know that the indefinite integral of f prime of x dx is equal to f of x? Or, better known as the fundamental theorem of calculus, how do we know that the integral from a to b of f prime of x dx, this definite integral, how do we know this is equal to f of b minus f of a?
Baby, can you move the chair?
That is what we'll get to next time.